No. All right, guys, what we got? Who's got the question? Yes.
22 and 25 of chapter 8.
8 point what? 3. 22 and 25. All right, let's see. So pick one of those. Which one? I love that. Showing off your knowledge of pick one. 25 is shorter. I want it down. It's less to read. Let's see. So number 25 in section 8.3. So this is the section about testing a proportion. So finding p hat, testing that against some known value of p. A survey of 427 women showed that 29% of them purchased books online. Test the claim that more than 25%. So the same thing I try to teach my algebra students about when you read a word problem, you don't try to take it all in. All you care about when you first read a statistics problem is a hypothesis problem is what's the claim. That's where that starts everything off. So what is the claim in this case? Oh, okay. Help the person out that asked the question. Nobody has a book. It's awesome, anxious. If you have the book in the room, open that bad boy up to page 404. Number 25.
You got 29% of them purchase books online.
Yeah, so they talked to 427 women. They got 29% of them purchased the books online. And the claim, more than 25% purchase online. Come on, worse. All right, so how do you say that in Mathish? The claim. Yeah, P greater than 0.25. So which one's that going to be, HO or H1? HI, yeah, okay. Right, and of course, why is it that one?
Because it's not equal.
Because there's no equal sign in it. So there's nothing about the claim has to be either one. The claim is what it is, and it gets put where it's got to go. If it's got an equal sign in it, it goes in HO. If it doesn't, it goes in H1. And HO, of course, is going to be?
Less than or equal to.
Yeah. I can't remember the book. I think the book always makes that equal to. The book is screwy. I don't agree with it. It doesn't make any sense. I mean, it doesn't allow for a claim to be, so this would be like a claim of, we think it's at least 25% or something, right? So the opposite, or at most 25%. So the opposite would be greater than. Yeah?
So what's the hypothesis? Is it greater than 0.25?
There's the claim.
Yeah, there's the claim.
The claim is it's greater than 0.25.
Right.
And then the two hypothesis statements are those.
Okay.
Yeah, the claim goes here because there's no equal sign.
All right.
Cool.
All right. Oh, yeah.
So there's always two hypotheses to it.
Okay.
Two sides to the argument. Yeah.
So on the quiz that we just had, you wanted us to put HO, H1. Those are the hypotheses? You didn't want us to write anything out?
Yeah.
This, yeah.
Yeah.
Okay.
Cool.
I did both. I wrote that out.
I was the same way.
And then I wrote out a little statement saying what that.
Cool. I like it.
Well, it's the hypothesis.
It's all right. All right. Don't give me too much to read. That's one reason why I don't teach English. So much to look at. Okay. What about, so one tail or two tail test? One tail. And of course, I'm just now remembering that there are quite a few of you who weren't here last time. Really bad class to miss because we're going to get it back into chapter 10. So don't only forget you need a handout from last time for chapter 10 before we do that. This is old news though, chapter 8. So it's one tail. What about the second step? What's the second step? Yeah, good. And the book doesn't exactly ask it in this order, but if you do these 5 steps, you will answer the same questions the book has for these kind of problems. And you want to get used to these because this is what I want. So number 2, can we use Z or T? What do we have to check in this case?
N is
N is greater than 30.
NP.
Yeah, it's an NPQ problem. I got to check to see if NP and NQ are bigger than 5. So what's NP? What's N? Is that trying to be 427, Jeff? So 427, what's P? 0.25. That's P hat. Right? And I always use the proportion of the population if I have it. And I'm always assuming in a hypothesis test that this is the real middle. So everything I do after that, I'm going to use that. I'm only going to use this when I'm making a z-score. Every other time I'm going to use this guy. So a fourth of this is almost 107. So that's bigger than 5. And then NQ would be 427 times 0.75. That's like 320 something. That's bigger than 5. Check. Which means what?
Normal enough.
Normal enough to do what?
To use these.
Z-scores. Now what would I do if either one of these was less than 5? What would I do then? Not a t-score. Because then it wouldn't be normal. So what is it about NPQ problems? It's Z or nothing. Yeah, it's normal, so you can use Z-scores, or it's not normal, you can't do shit. Because with an NPQ problem, I always know sigma. Right? We're assuming we know the population proportion, and that's what creates sigma, isn't it? It used to be square root of NPQ. Now it's square root of PQ over N, but it's the same idea, right? Do you guys understand that? So it's not a question of do I know the standard. I always know the population standard deviation for an NPQ problem because I'm assuming that's the population percentage. So the standard deviation I get will be the population standard deviation if it's normal enough. If it's not normal enough, screw the whole thing. Can't do it. At least not in statistics 1. Let's see. So I can use z-scores. So now, what's the alpha in this problem? Did it tell you?
No.
All right, cool. So I kind of warned you about this, right? I don't know if you remember. They didn't tell me any damn alpha, so I can't set up. There's no rejection region to set up. Because they didn't say anything at the beginning, right? No. I always thought that was a little bit evil. But whenever that happens, normally on step 4, it's going to be something so extreme. It's going to be like 10, which is stupid. It's going to kill any test, or 0.7, which is like, that's never going to beat any test. It's so close, right? So it's going to be some extreme. It better be, or else this whole thing is. Let's see what the book did here. So what's my p hat?
125.
Yeah, because now I want to look at the sample and find, what do I want to find? Z star. So b hat, they just give it to me. I don't have to calculate it. Right? It's 0.29. Do I need q hat? No, I don't. Because I'm going to use p and q because I have it. So that's really all I need. So then the z-score, z star, is p hat minus p over square root of pq over n. Remember, we borrowed this from confidence intervals. This is the standard deviation for a sample within a binomial problem. It's kind of weird. That's why it's not the same as NPQ. But we kind of already did this for confidence. We derived the confidence interval formula. So I'm like, that must be the standard deviation for these situations, and that's what we use here. So what do we get here? We get 0.29 minus 0.25 square root of
0.25.
good 0.25 times 0.75 divided by 427. And then whatever that is. Yeah, I'm trying to do my head. 140. 4.01. Please save me. Thank you. Huh?
1.909.
1.909?
We have 1 point. Yeah.
Okay,
Nine,
okay.
one.
Got a verification there. All right. So from that answer right there, can you give me a rough answer? Can you give me Rough conclusion. Not the actual conclusion, but what do I know I can do? Did we make it in, do I know anything? No. Oh, this is really evil. Why did they do this? Oh, that's so funny. Sorry. Not only do they not tell you alpha, but they don't have the answer in here either. That's really evil. There's no answer. There's no answer.
There is no spoon.
Yeah, that's right. There is no spoon. So what we'll do is we'll use the most used one, which is 0.05. Use alpha 0.05. So let's do it this way. We couldn't do this at this point because we didn't have an alpha, so we couldn't really make a rejection region. So can you give me the p-value for that? What's the p-value for that situation? I love the way you guys look at me like, maybe you should have told us what that is. We've never talked about such a thing. Expressions have such a massive way to communicate with me. So we're in this situation. Here's my 1.91. The p-value is just 1.
Or the area.
The area
tail.
and the tail that my z-score makes. Right?
0.025.
So if you look up 1.91 and do 1 minus, you get
1.91. Sorry.
point what?
0.28.
281, yeah, good. So remember, how do I check p-values? The p-value's got to be how related to this?
Gotta be less than?
Got to be less than. So if the p-value is less than that, we can reject the null, support the high. Okay, maybe.
So we're just assuming the alpha is...
Yeah, now that was really evil for them to do this. I can't remember if maybe somewhere they say, because 0.05 is the most often used. So they might have said somewhere, if we don't say it, then use 0.05 because it's the most often used. But I don't know if they said that somewhere. I was not expecting that. They're evil. All right, anyway. So that's the most often used one. If they don't give us one, then you can use this if they don't tell you otherwise.
Okay.
And in this case, I definitely have something less than that. So we've rejected the null. Support the high. Because again, real quick, if the alpha is 0.05 of a one-tailed test, it's a z-score. Can somebody tell me what the critical z would have been on step 3?
1.96.
You sure about that?
No.
No, you shouldn't. If I have an alpha of 0.05, one-tailed test, it's one tail, not two. Oops. Yeah, there you go, 1.645. So now you can, and that's a little more visual. 1.91 would totally be inside there, right? It would be in the rejection region, so it matches up with our answer there. But the p-value test is just as quick. Find the p-value. If it's less than alpha, you reject. Because that would mean you must be a smaller tail. That would mean you must be inside this guy's rejection region. If it's not less than, then you fail to reject. So how do I word my conclusion? Yeah. You kind of ran out there.
Sufficient evidence to support the claim that more than 25% purchased online.
I like it. Sweet. What he said. So we've definitely found, we didn't fail, so we have found sufficient evidence. We found SE to support the claim more than 25%. I think it was all about women purchasing books or something, right? Yes, that's exactly right, Jeff. Wow. More than 25% of women purchase books online. I definitely do, man. Get the Amazon card and just buy so many books. You never finish reading the damn things. That's what I do. Giant stacks and just like, someday I'll read that. So we have found sufficient evidence to support the claim, because again, the claim was H1. So I go right here, and this tells me what language to use. That's the step that really, once you get the other steps down, that step is always the one that's never quite firm. But there's no vagueness about it. You just say, which one's the claim? That's the wording I'm going to use. I love it when people say, we have failed to find insufficient evidence to not... So I'm like, oh my God. That is an English maze of stuff. Yes?
If our summary at the end said that we have not found sufficient evidence to reject the claim, is that the same as that?
No, because we did reject the claim. No. And we would never reject the H1. We never would. We either reject the null or fail to reject it. We support the H1 or fail to support it.
Okay.
So it would be, we have not found sufficient evidence to fail to support that. And then you're getting into the whole double negative, which in math is okay, but... All right. Maybe. Anything else from homework? Are you guys doing the homework? It's better to do that. It would make you feel better if you said yes. Thank you for the opportunity to say that. Sounds really good. All right. So if there's no other questions, we're going to get right back into chapter 10. And what I want to do is do one together with you, considering quite a few of us were not here, just to continue to throw that in your face. Whatever you were doing. So we're going to do one out of the book, and considering again that not many of us have that resource. You could bring your tablets and access your ebook if you want to. All right. Bring your Google shirt and have it show up here. Thank you, Google. I don't know. They got Google glasses. What the hell are they going to do next? I keep joking about Google. Take a look at this. What's the answer? Okay. You guys check the clothing you're wearing. Let me see. That's Google. Get it over there. Get it. All right. So this is on page. Let's do page 501. We're going to do this cricket problem. So I don't know if you guys have ever heard of this. It's actually semi-true, depending on the kind of cricket you're listening to. So if you don't know what kind of cricket you're listening to, you're not sure which formula to use to figure out the temperature, I'd rather just check my smartphone and see what temperature it is. I'm not Bear Grylls out there. All right, guys, so let's do this number 24. It's not very focused, is it? Crap, I have. All right, that's better, I guess. All right. So, how am I going to do this? If you have your calculators, go ahead, and even if you weren't here the other day, you can put the chirps in 1 minute. You can put that in list 1. And put the temperature in list 2. And then we'll do this stuff together. I think I got mine set up yet. I tell you now, it's not, the data they used is not really near the actual equation used, so I was a little disappointed. I don't know if this is real data. Knowing the author, it's probably real data. Song of Basics. All right, there you go. All right, how we doing? Has everybody got that? Anybody still need that up there? All right.
What's that?
Oh, while you guys are doing that, who needs that chapter 10 handout from last time? Sure, it's got 2 sides to it. Have y'all seen that? All right. So now everybody should have that, right? Okay. All right. So you got your data in list 1 and list 2. One thing you could do is you can go to second y equals. If you were here last time, it should be set up for this. So the first one should be turned on. This is all statistical plots. So it makes sense to go here. I want plot 2 and plot 3 turned off. So if any of them are turned on, you can just go to number 4 and turn them all off. And then go back second y equals. Go into number 1, hit enter. And then when you're on, hit enter. Make sure that this one's picked. We're going to make a scatter plot first. So we can do, we've done scatter plots before, way back in chapter 2, I think it was. And once you plot them, you can see if there's any kind of trend. We only focus on linear trends, although there's a lot more than just that. Make sure it says list 1 for your x's, list 2 for your y's. Pick which one of these you want, a square, plus sign, or a little speck. That's just to mark your data. If you hit graph, you probably won't see much that's left over from last time. Poor little dude. Go to y equals and clear that out. So of course, what do I have to hit before I can see my data?
Zoom 9.
Yeah, zoom. And normally it's 9, I don't know, depending on how beefy your TI is. Some of you guys have like these long ass lists of stuff you can do. So it's zoom stat, whichever one that is under the zoom window. So for most of you, it should be zoom 9. So let me know if anybody is not able to get to this point here. I should hit zoom 9. Weird. Oh, look at that. You got a little butt graph. Okay, let's see. So you take a super. Alright, so take this all back to normal. Alright, so now if you hit, and do you have this guy turned on? No, so the plot's going to be turned on. Now hit zoom 9. Okay, so whenever you put new data in, you have to hit zoom 9 and the calculator will find it for you. Funky dog. Oh, it's 72.6. I don't know if it'll change that. Yeah, now it's zoom in. I hit zoom in. How's everybody else? You good? Good one. Great. Wow. Good. All right. So, if you were here last time, you might already have the line of best fit up there. So, if you weren't here last time, and just to remind everybody else that was, does this look like a pretty good trend? Is there a really strong trend? Kind of. I mean, it's definitely, if I drew a line, there would be almost no question about where it goes. Right? So I expect the number that represents how strong the relationship is, how close the points are to lining up directly on a straight line, I'd expect that number to be close to its maximum, or not close, but maybe around 0.7, right? Maybe a little less than that. I don't know. We'll find out. So that's the whole idea here is, number one, how tight are the points to being on a line, and that's captured by something called the correlation coefficient, or the Pearson product, right? And the guy who taught me stats, his name was Pearson, no relation. You like to pretend he was. What am I trying to say? And then secondly, I want to actually get the equation of that line. And it's really cool. The line is a visual average of where all the points are. So I love that idea. R is sort of a standard deviation in a way. Even though those values are from -1 to 1, that's not what standard deviation does. But it's still a measure of how spread out the data is from the average, which is the middle line. Cool? And I know we don't get a lot of hurricanes in California, but have you ever seen that cone of uncertainty when the hurricane, have you ever seen that from the, I don't think there's any active hurricanes out there, but I used to live in Florida and Virginia, and hurricanes were just a part of life. But you see this little, here's the hurricane, and then it's got this cone of uncertainty. You can do a better job, Jim. I don't know if you can, Jim. And then right down the middle is this little line, and that's like the average, that's the most likely path. But then they have kind of a spread of where it might actually go out. Because, of course, weathermen are like, what do you want from me? Shoot. So a little butterfly flaps his wings here, supposedly, and then, things happen. Okay. So I want to find out where that visual average is. And I also want to know what the real strength of this thing is, the correlation coefficient, how strong this is, how tight this is to a line. So where do I go for that? Stack? Count. And then it only makes sense, the one that actually has the equation of a line. Now, of course, statistics has to be different from algebra, so they don't use M, they use A. Right? We're not algebra, we're statistics. So, number 4. And it defaults to list 1 and list 2. So as long as you put your data there, you just hit enter. So I don't know, this is what I get. Look at that, it's stronger than I expected. Is that what you guys got? All right, so that A value is the what of the line? Slope. And the B value is the y-intercept. Keep up. All right, so R squared actually, R squared is, right now we can look at it sort of like sigma squared. It was a middleman. But to be honest, R squared is sort of like the percentage of the change in Y explained by the change in X. So remember how we talked about, if you weren't here, you don't remember, but we talked about how temperature, if temperature changes, it can change the price of H2O and the price of ice cream. So you might think that those two kind of relate to each other. But there could also be, maybe there's a brand new ice cream flavor that came out. That would affect the sales of ice cream. Maybe you're having a sale on your H2O. Or maybe you have this H2O that supposedly cures cancer. That would maybe, change the sales of that. You kind of with me? So there's all kinds of variables. So at any point in this kind of test, we're only testing 2 variables against each other, right? I don't know if there's something else. So the R squared is an interesting number. It's 76% of the change in the chirps. Or I can't remember which way this is. 76% of the change in the temperature could be explained by the change in the chirp rate for this problem. All right, so that's saying that there's 24% unaccounted for. But even that could be something behind the scenes controlling both of them anyway. But this number right here tells me, yes, they are very strongly correlated. And we just go straight to R for that. Now on a test, I have to tell you, like I said, I have to tell you what R value is enough evidence. I don't think in this problem they really tell you. No, they don't. So we look back at that table. Or I'll look back at the table. Let me see. I'll try. Here it is. So how big was our sample here? It's 3, 4, 5, 6, 7, 8. So for sample size 8, we need at least 0.707. Oh, you can't see that, can you? I love this. All right. So for sample size 8, 0.707 or even 0.834 if we go for the stronger test. And we got 0.873. So either way we look at it, we have evidence that there's correlation. Okay, maybe. So in a test, I'm just going to give you that cutoff number. That's related to the critical z-score. This z-score here. This is related to this. So then I take a sample, the chirps and the temperature, and I just see where it fell. And our sample fell above that. So that's evidence that there's a correlation. But remember, every damn thing you do in statistics, there's always behind the scenes a chance that I'm wrong. So if I use that higher number, I still found evidence, but there's a 1% chance that I'm wrong, that there really isn't a correlation. That's what you love about stats. It's just so honest. Right? It says, it looks like this, but I don't know. It has that kind of accent. It's weird. You never think that statistics would tell it. Okay. So where'd the problem go? So if you're doing problems out of the book as opposed to online, the problem with online is they keep changing all the data. So I think I tried, if you do section 10.2, you want to do section 10.3 at the same time, because I'm pretty sure I tried. C24 is again crickets and temperature. So for me, for a test, I'm going to make you come up and show me the line of best fit. So you actually have to come up and show me this. Not that, Jeff. This. With the line of best fit on there. So somebody help me out. What was the line of best fit again? Can you write that down?
Y equals
0.5x.
Okay,
0.05x.
plus 27.6.
I like that. Repeat it. Let's see. So that's the visual. It looks low. That can't be right.
I went out to
27.67. Yeah. 0.05. Let's see.
0.0523
0.0523. Yeah.
plus 27.628.
That's better. Yeah. So this doesn't have to happen, but I don't know if you guys could understand. Do you understand why I felt the way I did? It was almost obviously too low. There are only 2 points below it. There doesn't have to be an equal number of points on each side, right? Because you could have one point that's really far away that kind of drags it up a little bit. Like you could have one value that's really high that would pull your mean up a little bit. But at the same time, it should be roughly equivalent, especially if the points are kind of semi-close. There should be roughly the same amount on both sides. Okay, maybe. So here's the next cool thing. This is, how wide is this window? What was the lowest number of chirps in that data set? Looks like it was 864. And the highest number of chirps was 1,200. So I can use this. Do we trust this line to make predictions? Why would we not? What tells me if I trust the line or not? The R value. Was the R high enough?
Yeah.
All right, let me ask it again. Do we trust this line to make predictions?
Yes.
Yes, because the R was evidence that there is correlation. Yes, ma'am.
How do you figure that out again? Was that the little table that you...
Yeah, and again, you don't have to look at the table ever. On a test or something, I'll actually give you the R value. That would be the cutoff. It's sort of like me giving you this. And then you just calculate the R and compare it. Now realize that if the R is 0.7 and you get an R of negative 0.9, that's good. It's like an absolute value idea because it goes both ways. There's no negatives in the table, so it just has to be further away from 0 than that. Maybe. Because what's 1 mean? R of 1, what does that mean?
Positive.
Really strong.
Really strong? Strongest? Perfect even. Positive correlation, right? So it would be a positive slope line. All the points are exactly on that line. And of course, negative 1 is just the opposite. I think for you guys, it was the reverse of that. You guys semi with me here? So the closer our R is to 1 or negative 1, the closer the points are to the line, the more I trust the line. The only problem with this one is it's a relatively small sample size, but it still beat the benchmark. The benchmark was freaking 0.8 something because it's such a small sample. It has to really show a lot of evidence. Very much like this would be the same if the t-score, if it was a really small sample, I could get a stupid big t-score. Really hard to pass that test. Okay, so here's the key. If you had a cricket and you were listening to a chirp for a minute, I don't know how you would do this. You count 920 chirps. You got to be really bored and really good at counting. Watch this. It's kind of cool. You ready? Some of you guys might know this from your algebra class. It's second trace. And you can do all this weird kind of stuff, but I want to do the first one, value. I want to know if the chirps was 920, what would the temperature be there? The temperature would be almost 76, according to this equation that we found. Right, so something, the calculator's got the equation in it. We put it into y equals. So it's just able to just plug an x in there. Ooh, that's how I plotted the line, right? So that would be my prediction. So when the book says, what would you predict if you saw 920 chirps? In fact, it should say something like that on this problem. What's it say? Oh, okay, they went a little evil. So maybe you can answer this. The book's question is, find the best predicted temperature at a time when a cricket chirps 3,000 times in a minute. What's wrong with that? I mean, you could do it. But here's what's interesting. If you try to do it, try to do that in your calculator. Yeah, if you try to do it here, second calc, value, you put in 3,000, and it says, what? And of course, the reason it is because it can only do that for values that are actually on the screen. And like we said, the highest, that's an interesting way. The highest, the highest value for the chirps was 1,200, right? That was our biggest chirp value in our data. Maybe. Plus, but what's more importantly wrong with that is our data only ranges here. If I want to know something beyond this, I have to wait until that cricket starts. I have to wait for it to get hotter or colder if I want it to be down there and listen. I got to get more data that goes out. Any prediction is only good within where the data is. So it's kind of cool the calculator is not able to do that. It's reinforcing that idea. It says you can't do that. It's outside this range. So maybe. You could still take 3,000 and plug it in here, right? You just plug 3,000 in there. But what's wrong with that? At some point, it's going to get hot enough, this poor little cricket. Maybe this is the intention. Somebody's going to eat the cricket. Right? They want it fried. And it's just chirping away. Chirp, 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 chirp. And then, it's flatline out there. Right? So have that image in your head for the rest of this. Yummy. So it's only good. I don't know if it gets really, really hot, if it starts to slow back down. It's like, oh, dude, someone cricket out. Oh, dude, it's just too hot, man. So I don't know if it's going to start to curve down. I have no idea. All I know is it's a line within that data. Are you guys with me? Now, what the hell? How do I answer the question if it says, give me the predicted value, but I don't trust the line? What if R would have been 0.5? Would we have trusted this line? No. So then the best predicted value, we know it's been the phrase I've used since we learned it, the point estimate. The average. I would just take the average temperature, and that would be my answer. I take the average temperature. What's your best guess at something? It would be the average. What's the expected value of something, which is your best guess? The average. I love it. Right? So I really want you to understand this is what's happening. The average is almost always my best guess at something. By doing this analysis, I am improving on that best guess if I'm allowed to trust this line. Now I don't have to give the average. I have a prediction for what the real value is. I don't have to just always say the average. You guys kind of with me? So if I said I just got a new car, which I didn't, I actually just got new tires. I just got a new car, and I said, what do you think the cost of it was? The best you could do is kind of come up with like an average car price that you think a teacher could afford, right? You kind of with me? That would be your best guess. But when I do this analysis, I could do better than that if I can trust this line. So if R is big enough, I can use the line. If it's within the range of the data, like the 920 thing was perfect. It would have been 70 whatever degrees. If R is not big enough, I have to go back to the guess being the average being my best guess. Yes.
So could you essentially just plug in 3,000 for X and your Y?
Yes, you could. That's exactly what they want you to do. I mean, the calculator thing is a shortcut. If the calculator thing doesn't work, it's telling you that there's a problem with it because it's not in the range of your data, but you can still do it. You can still plug a 3,000 into that equation. Of course you can. And what do you get if you do it?
I would love to tell you in just a second.
That would be awesome.
$184.5
Yeah, the cricket is in a sauna or something, right? Sauna. I'm part Finnish. She went to Finland and was in a sauna with all these naked old guys. We were beating each other with the birch branch and everything.
Oh, wow.
That was an experience.
It sounds like it. So you almost sound like the
It's
machine.
burned in my brain. Okay, so what I want you guys to do, let me give you this. Here's the practice test. I want you to go ahead and do number 5, which is the correlation regression problem.
So Jeff, would you rather us just find the average temperature or plug in 3,000?
So the book wants you to plug in 3,000 because then they ask you what's wrong with this. And you say it's out of the range of the data. You couldn't even use the average because it's out of the range of the data. I would use the average if it's in the range of the data, but my R value is too low, so I don't trust the line. Yeah. So number 5, this is actual data. It's from the year 2000. Whenever I say that, I remember Conan O'Brien. Huh?
What about Conan?
No, Conan O'Brien.
Yeah, what happened to Conan?
Oh, he used to have the bit in the year 2000? Before,
A
well,
little before my time, I guess.
could be.
Yeah.
If you're under 20, then you were under 6 years old at the time, so I don't think you were watching Conan O'Brien.
Wants to do number 5?
Number 5, yeah. Go ahead and start working on it. Call me over if you need some help.